In this video, I'm going to explain a little bit about MATLAB and Simulink, what they are, why we'll be using them in this class, and then also give you a short example of how you can use Simulink to solve or simulate a control problem. So why not use Microsoft Excel? Microsoft Excel is excellent for visualizing data, especially in a tabular format. It's also excellent for static systems, but it is not excellent for dynamic systems. So in this class, we're going to be dealing primarily with dynamic systems, with differential equations, and Microsoft Excel is not the preferred tool. Your homework and labs will require you to use MATLAB, and there's a good reason for that. MATLAB has a rich library of math functions and capability. It's basically the control design tool used in industry. MATLAB has an easy-to-use scripting language. So scripting language, basically that means you can write a program that will over and over just do the same. That can do the same thing. So you can write a computer program to solve your problem, and then if you come back to it, it's very easy to revise. Or if you have a similar problem to solve, it's very easy to reuse your script. Simulink is almost like a sub-program within MATLAB. It provides a means to graphically build a model of a physical system, could be mechanical or electrical, as well as the appropriate control system. So you have the physical system and the control system modeled together. Simulation capability to allow the evaluation and optimization of mechatronic systems. So you can run your system, run a simulation, and change parameters on the fly, or it's very easy to run a few simulations and quickly determine what range, for example, of control parameters you need to be using. Simulink is widely used in industry. I use it every day at my job at Chrysler. And controllers implemented in Simulink can auto-generate code for the target processor. And this is also very, very common in industry. So you should learn to love MATLAB and Simulink for this class, and also if you intend to do anything in the industry with mechatronics, MATLAB and Simulink are just phenomenal tools. Let's do a quick example. Here's we're designing a control system for positioning a GPS satellite in orbit. Okay, so we're going to do a one-dimensional part of that, right? We want to change the angle of the satellite. We want to kind of point it in a different direction. So we have a desired angle, and we can measure the actual angle by using a gyroscope, a gyro sensor. So, and we have a pair of chemical thrusters. That's these here. There's applying a force on both sides. So we have the force to apply. That's our actuator. We have a gyro sensor. That's our sensor. It converts angular position into voltage. Okay. All right. So how can we model this in Simulink? Well, first of all, let's break this down into a rigid body motion problem. Nice thing about a satellite, first of all, it is almost already a free body. Okay, so we're going to have two different torques here. We're going to have one that is from the thrusters, that force marked F, and we're also going to have another friction torque. Now, there's not much friction in outer space, but things do eventually slow down, so let's include that as well. So we have 2 times the thruster torque minus the friction torque, and that's going to be equal to this value J, which is actually the inertia of the satellite, times the angular acceleration. So this is just F equals ma, but it is angular instead of translational. All right. So this value T friction. Not sure. We need a way to do that. That is going to be modeled. This is a linear model that we'll talk about much later, or much more later in the semester. But essentially, the friction torque will just be a constant times the angular speed. Okay, so we have our thruster torque, we have our friction torque. Now let's get our thruster torque. So we have a force being applied by that chemical thruster. So 2 times F times R. Of course, this distance right here. This is R. Okay, and I guess I should include on here this. We have a torque going this way. This would be my T friction. Okay. Oh. All right. And now we write the equation of motion. Okay. So inertia times the angular acceleration. And then I brought the friction torque. Here's the minus sign here. I brought that over so that all my terms are positive. Okay. And we have an equation of motion, just like that's just Newton's second law. Okay. I want to solve now for my angular acceleration for the highest derivative, and we'll find that's useful later. Okay. So this is a dynamic system. There are derivatives here. This differential equation tells me how the acceleration is affected by the forces. Okay, but it doesn't tell me the position. If I want the position, I need to solve the differential equation. Okay. The nice thing about Simulink is that it can get an approximate solution to the differential equation to very complicated differential equations, and as long as you know this term, the force of the thruster, and you know the initial conditions of the position and the velocity, you can get an accurate simulation. Okay, so let's go ahead and build this in Simulink. Actually, a couple more things. So how does this actuator work? That's something we'd have to figure out. So here's the thruster force. The thruster force, we basically give the thruster a voltage command or a voltage input, and it generates a force. All right, with a constant kF. And we have a sensor, and the sensor is going to take a position and give us a voltage. Okay. So we, on the other hand, will have a desired voltage. So we have the same constant Ks, right? That has to be the same in both times. So we want, if we have a certain angle that we want, theta desired, then we need to calculate a voltage desired. Okay, so that we can compare them. So notice that these equations are static. There's no derivatives here. So if we know the desired angle, for example, we know exactly the desired voltage. It doesn't change dynamically. Same thing with the thruster. We're saying that as soon as we apply a voltage on the input side, the thruster voltage is just constant multiplied by that. So, okay. So we also need a controller. Okay, we'll learn more about designing controllers later in the semester, but for now, let's say we have this. Okay, our controller is just equal to a constant. Okay, let's go ahead and make a block diagram. Okay, so in Simulink, it looks like this. Okay. The way you do this, you might pull up MATLAB. Okay, and you can just type in Simulink. And it will bring up your library browser. This is the button to create a new model here. And what you can do is you can drag blocks. Okay. Commonly used blocks, you'll find a lot of very useful things here. You'll notice I'm going to use, in the next model, an integrator. Another one that will be very useful is a scope integrator for solving differential equations. The sum is a very useful block. Anyway, I'd encourage you just to play around with some of these. Now I have created a model I'd like to explain a little bit. So it looks a little complicated, but basically what I've done, I have two integrators here, okay? And the integrators, I start off with my acceleration, angular acceleration. I have angular speed after I integrate it. If I integrate that, I get position, okay? And basically building this model means I need to find out where to put the terms, okay? And these can be very physically. I like this because I can give each of these signals a physical meaning. So acceleration, that's just my net torque divided by a constant J, okay? So if I put my my torques together here, remember this last slide here, okay? So thruster torque minus friction torque, I add those, or I add those together. This one's a negative term, and then I'd have to divide by J, and I get my angular acceleration. So here's where I'm adding those. Here's the net torque, and then here is the division by J. You'll notice also here's my input gain, because this is, so the thruster torque is the voltage into the thruster times that constant. Here's where the controller sits. Here's my desired position, which I'm converting to a desired voltage. Here's the actual position, which I convert to a voltage so that I can compare the two. Okay, so I can run this by hitting this button. It changes the amount of time you run the simulation for, and there's a lot of other ways to configure. Then scope allows you to actually see the output. Okay, you can click this button here to make it the auto scale to see exactly what you want to see. Okay, so here what we see is initially I wanted an angle of 0 radians, and after 10 seconds I said no, change the angle to pi over 4 radians. Okay, and you can see that it takes the satellite a long time with this control system to reach the steady value, but it does. But one thing about this is that that's okay, because for this application, for a satellite, we don't need to be positioning in microseconds. If we can just keep the value rock solid, that's good enough for this. Okay, so that's a quick example of how to do this. And if you have questions on MATLAB or Simulink, please let me know, and we'll because it will be a tool you'll use very much in this class. All right, thanks for watching.